All right, so last time we talked about Newton's method, and we talked about how it was, you were trying to find the root. So they told you on this homework that there was a root here, and there was a root here, and there was a root over here. This one was what, negative 1.88? What was this one right here? On question number 3. In your book, what does it say? What's that? 0.35, and what's this one? 1.53. So it said there's 3 roots, okay? So it says if you choose 0.95 as your first root. Now here's as your first guess. So this is just to review this. Now this is something I would want you to be able to do on this next quiz that we have on Friday. If I ask you a question about Newton's method, it will be not doing the table, not doing calculations. This quiz on Friday is no calculator. I want you to understand the process of what it's trying to do. Okay, so number 1, Newton's method is a way of finding the roots of a function, where the function is equal to 0, where its output is 0, which is where its graph crosses the x-axis. You got to understand that first. What is Newton's method trying to do? It's a method for doing what? It's a method for finding the roots of a function. Okay, so you got to know that. How's it do it? Writing the tangent line is the idea. So in other words, we think there might be a root right here, 0.95. That's silly because we're looking at a graph. But what if we weren't looking at a graph? What if we just had the equation, right? We think there might be a root of 0.95. Well, it turns out that that's right near the peak. That was the idea on this one. Now, we can argue all day on which one this was going to be. Now, the answer book, didn't the back say this one? Did the back say negative 1.88? Emily, isn't that what you were telling me?
Yes.
Okay. So, but you could argue that is the argument here. That's the idea. And they want to know what's happening. Well, one of the things we talked about is if you make a guess near a peak, it's going to be a real shallow tangent line. Okay. Now, this tangent line, so one could argue that this tangent line is so shallow here that it would shoot me over to here. And then what does that matter? Well, what does Newton's method do? We remember what we did last time? We took the tangent line equation and we set it equal to 0. We took the tangent line equation, set it equal to 0. That is, we saw where it crossed the x-axis. Thinking that, most of the time, near a root, the tangent, if your guess is close, the tangent line will cross the x-axis about the same place as your root does. Right? That's the idea. But you got to have a good guess. You got to be in there close for that to happen. Well, if you pick one where it's not close to a root, where it's at a peak like this, it could shoot us off to here. And then we put that in, and we do that tangent line, and that shoots us to there. And then we put that in, and we get this tangent line down here, and that might shoot us up to here. And then that tangent line, and boom, eventually we would find this root right here. Now, I could see someone arguing when they draw their tangent line here, they drew their tangent line like this. Now, what if it would have landed there? Now, this tangent line maybe is going to take me back over to here, which might take me over to here. You see what I'm saying? You see how that, depending? So the idea is very little change right here in where my first guess is could determine where that next line, it's actually not the first tangent line, it's sometimes the next tangent line and the next one. Because if this one shoots me far enough to go past this peak here, right, then I'm going to start being on this end and I'm going to find this one. If it shoots me here where I'm on this side of the peak, if this first one took my tangent line to here, then it would probably go down here and I'd find this one. Right? If this took me near the peak just enough to shoot me way back over here, then I could be finding this one. So there's a term for that. It's called sensitivity to initial conditions. A very small change, especially when I'm by this root, could really change where I end up on this one. Okay? But you got to understand just the basic process. The basic process is we pick a point on the function, hoping it's 0. If it's not, we ride the tangent line down to the x-axis, use that as our next guess, ride the tangent line down to the x-axis. Usually what will happen is the tangent lines will get in here close, like what we saw last time on that Sketchpad document where we saw those things happen. Okay, so that was the idea number 3. Okay, now number 5. Number 5 is where you're actually supposed to get into this. Were you guys getting some numbers like this, 0.706? 0.706 should have been, I didn't fill in all the other numbers, but, okay. Now, you're not going to have to do this on that quiz here, but you might have to do one of these on this take-home. So you want to have this in your notes, right, where you can do this. So what'd you get when you put in, did you guys start with 0.5? I kind of suggested that. So what'd you get here from 0.5? Let's just fill in a few of the numbers. Jesse, go ahead and just tell us.
-0.960.
9 what? Okay, Emily, were you getting that?
I started with 0, and I just got to 0.75 from there.
So you got to these numbers eventually, though?
Yeah.
So your numbers will look a little different here. Okay, sure, yeah, if you do a different initial guess, it will. Okay, then what'd you have here, Jesse?
4.312.
And then you divide those, and that gives you,
-0.22.
okay? And then you take this, subtract that, and it's that right there. Okay, and then that becomes your next guess, 724, da-da-da-da-da. Tell me what you got here. 0.09. Now, we're hoping that that would be 0, right? Well, it's getting pretty close, right? We plug that in. Then we plug that into our f prime. What'd you get there?
5.3.
And then you divide those.
0.01.
0, 1. And then this, subtract that, and I got this right here. Okay? And then we bring that over here, and we don't need to do any more, but boom, boom, boom. Well, notice we were only supposed to do 3 decimal place accuracy, right? So you could have stopped right here, right? 0.706, 0.706. Okay, there you go. So we were doing that one. We had a whole bunch of steps we had to come up with before we were getting it, but here we go. Okay, everybody get your calculator out, and we do need little hats on here, so take a hat and pass it around. So that's just your table method for this. Okay, and that was part A, I think, in the homework, right? You were supposed to do, I said, and find the solution. Okay, so 0.706. Does this equation have any other solutions? Justify your answer. So here's where I want to show you a shortcut for this. So let's let you log in here. Just. All right, here's what we're going to do. So, go to your calculator screen, okay, and we're going to do number 3 here. So you're going to define your f of x to be that function. So we're going to go to under menu, actions, number 1 there, define. Now, everybody's going to want to do this because also on that take-home, you're probably going to have to do this. Not on the other one, but on the take-home. So you're going to want to, or else make sure you study with someone who knows how to do it. So we're going to take our original function. We're going to call it f of x. So put define f parentheses x. equals, and then what was our function? X to the fifth plus 4x minus 3. So we're gonna, we're gonna do a couple different little shortcuts here. I'm gonna show you a shortcut, and then I'm gonna show you the super duper shortcut. Okay, the super duper shorcut's really cool. Okay, hit enter. Now we're gonna define our derivative to be g. Okay, so we'll just remember that g is gonna be our derivative. So menu 1, 1, menu 1, 1 is defined. Menu 1, 1. Define g of x, and that'll be our derivative. So that'll be 5x to the fourth plus 4. So we always set this up ahead of time. So we got our f and our f prime, right? So we got f and we got g. Okay? So now, we want to start with a 0.5. So let's recreate that. So we can recreate this table that we had here. So go do f of 0.5. Now, to be honest, if I was doing this, remember I showed you this with the vertical bar the other day? We did it on Friday, we did it with the vertical bar, where you can do the vertical bar. Well, I think this is faster, right? I think this is probably even easier, but whatever. So f of 0.5. So if Jesse was doing his table, okay, so there's that number. Now, how come you're only getting those decimal places? Oh, that's probably exact, I guess. Probably. Okay, so if we go back to the table, Jesse told us negative 0.968, and that's what, sure enough, that's what we had, negative 0.968. Okay, and then we go do g of 0.5, and then we want to divide those, right? So we're going to go up and grab that one, divided by that one, okay? And then we're going to take our original, which is 0.5, and we're going to subtract that up there, and that was that right there, right? So that was our original 0.5 minus that, so forth. Okay, now, here's where we could have done that a little faster. Instead of, now, since we're doing the table, we needed each one of those, because we need to write that down, need to write that down, need to write that down. Okay, now, we want to take that number and plug that in, right? So now we want to do f of that. We won't go through it, but we can do f, go grab that, that'd be f of that, then we can do g of that, then we can divide it, right? And that's how we can fill in our table. So that's kind of a shortcut, okay? Now, I guess a super shortcut would be if we're not doing the table, right? If we're not doing the table and we just want to find some other ones. So they said, are there any other roots? So let's try like 3 as our initial guess. So this time I want to let's go ahead and type the whole formula in, right? Let's start, we're not going to do every entry in the table. Let's just type this in right here, right? So Jesse, what would we type? 3, and we want 3 to be our guess. So we're going to go 3 minus, okay? Now I hit control enter. There you go. All right, now that's 2.38. Now we want 2.38 to be our next guess, right? So one way would be to just go up and grab that right now. And so go ahead and do that. So one way would be to just go up and grab that and then minus, and then f, do a fraction, and then f parenthesis, and go up and grab that. Now here's where it gets a little tricky. Here's where we ran into some trouble. I've run into trouble. So go g parentheses, and now you want to go up and grab that, hit enter. Yeah, see? It doesn't stick it back in there because when you up arrow it, it put it right there. So go ahead and delete that out of there. So that's where we ran into some trouble. Okay, so let's delete that whole line. Okay, so that didn't work very good. So do you have another idea where I can do this pretty quick? Yes, and do the vertical bar. So let's do x minus f of x over g of x, right? Because g is our f prime. And then do vertical bar, x equals, and then go grab it. Does that make sense? So this is like a super shortcut, right? It's a little bit of it was kind of a shortcut to just do that and not have to fill in all the tables. So that's a shortcut already because we're not doing all the table parts. There's our next case. Okay, so now what are we going to do? We're going to go grab that, and we're going to delete that. What's happening?
Now I
It's froze.
not on mine. It's like deleted that.
Okay, go up and grab the other one. Maybe it'll. So this is yours is working fine, but it's frozen. There we go. Okay, so now we got that. Okay, so interrupt again. Let's keep going. Let's keep going. And now we're just continuing to plug that in. Darn it, I was hoping it was going to get. Well, I'm wondering. It looks like it is, isn't it? Right? I have a feeling it's going back. So can you picture though? Here's the thing. Here's what I hope you're doing. I hope you're picturing this happening, right? What's happening is it's getting closer and closer and closer and closer and closer. We were out at 3, right? And now it's headed back to 0.706. Okay? So it's very much like this that we had the other day, where we had this one, and we said, okay, let's guess this one out here, and now it's giving us this number right here, that's our x2, and then we're plugging that in, and now it's giving us this number, and then we got this, and now it's giving us that number, and right, we're getting closer and closer, and it's just zeroing in, pun intended, right, on that root, Okay, and that's what we have happening right here. Okay, now, maybe you guys don't know, haven't used a calculator enough or know enough about this. There's something we can do here that would really make this. And this, of course, will be the super duper shortcut. This is kind of the super shortcut. But instead of having to go and grab that previous answer every time, look on your calculator. Look specifically at the equal sign, or no, it's near around the inner sign, inner key. Answer. See this right here above the negative key where it says answer? That is a variable that stores the previous answer. That's what we want. That's what we want to go in there every time. So, where would we put that in our little formula? Well, we could, or we could put it in here for the x. Let's see if x equals answer. I never thought about doing x equals answer.
It changes.
Yeah. So, but here's the problem. The thing we got to start with though. We got to put something in answer to start with, right? It's called seeding the calculator. We got to seed the variable. We got to give it an initial thing. So type in a 3 and hit enter. And what that does is that just puts that into answer. Now go ahead and try that. Go ahead and grab your x. Go up and grab that. And yeah, let's delete that and let's put answer there. I never thought of that. That would actually work. Or you could just go answer minus f of answer over g of answer, right? And do that. Okay, now hit control there. And then just keep hitting enter. See how it's doing that? You just keep hitting enter. Because what it's doing is it's automatically going and grabbing this, since we called that answer. And then boom, 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 we get to it right away. So are there any other roots? Well, geez, let's do some other guesses. Let's do 5 as a guess. So grab 5. No, not grab it, I'm sorry. Yeah. You're going to have to seed the calculator. So you're going to have to, as a first guess, I mean, 5. Yeah, now I don't think, now if you go and grab that, now I think you have to delete that and put answer.
Yeah, but it's going back to 3.
But it's going back to 0.706 again, you mean?
3, yeah, but 3 went back to 176.
3 did, yes, yeah.
Yeah.
So let's try 5. So now, did it freeze up again? God dang it. What's going on?
It goes back to 0.76. I was saying the first one went back to 3, so 3 went to 0.76.
Oh, it actually goes back to,
Like 3.99.
right. Okay. So you started this one with 5,
Yeah.
right, and it got you to 3.18, keep going, yeah, and then go down. And so it's just, so that probably is, maybe there is only one. You know, let's try negative, let's do one. Let's do negative 3. It's almost like when you delete a whole bunch of times, it's like it can't keep up or something. That's weird. There it is. Okay, so you put in negative 3. Okay, now do your answer. Okay, and it's getting it. Okay, now let's go to 15. So 15, you're supposed to find each of 3 roots of f to 5 decimal places. Now, if you remember, my directions for you were just to do that, just do a solve. So go ahead and do a solve on that one right now so we can all see it. So it's x cubed. You go ahead and do a solve, and I'll just say, so x cubed minus 10x squared plus 22x plus 6 equals 0. Okay. Okay, and there they are. There's our 3. Question?
So how would you know, like on that other one, so more than one?
No, you wouldn't really, not just by guessing. You'd probably have, I mean, there would be some ways, but we're not going to do that. Okay, all right. So here's the 3 answers, and we can scroll through there and find it. What happens when you put in a 2? Now, you were supposed to do one row of the chart and put in a 2. Well, what'd you get? Did you get like a 5? You get a 5. Now, I really only wanted you to do one row of the chart on that. Well, no, you have to do a second row, I guess. And then you do a second row of 5, and you get what? You get 2. Well, let's do our super duper shortcut here. So so type in a 2, okay? Type in a 2 and hit enter. And then, oh, we haven't stored that though as our f yet, have we? Okay, yeah, we gotta do that. So let's do f define, so menu 1, so there's a little bit of a setup here in the beginning, but it's still faster than doing that table. Yeah, x cubed minus 10x squared plus 22x plus 6. Okay, enter. And let's define g of x, so menu 1. And g, of course, our derivative, so 3x squared minus 20x plus 22. Okay, and now type a 2 and hit enter. And so now that's our previous answer. And now let's do the other way. Now let's just go answer minus f of answer divided by g of answer. So that's going to now hit control enter, so we get a decimal this time, but even though we know we're not going to get a decimal here, but hit control enter, you get 5, hit control enter, you get 2, and it's just going to bounce. It's just going to keep back. You actually don't have to hit control enter each time. So it's just going to 5, 2, 5, 2, 5, 2. Okay, and so that's, of course, that cycling thing we talked about where you plug this in, it takes you here, you plug that in, it takes you there, and it just keeps taking you back over and over to the same one. So you're not going to find a root. Okay, and then it says, now try to say something weird happens if you put in 1.39. So let's do 1.39, hit enter, then go answer minus f of answer over g of answer. Now what just happened? 1, a huge number. So what? What's that mean? What just happened? Yeah, I want you to think of this. What just happened? That tangent line just crossed the x-axis out here at 5,391. That's what you need to understand. On Friday's quiz, I might ask you a question to draw a picture of what just happened. Right? I could give you that question right there. Something odd happens. You don't have a calculator, so I would say, okay, we did Newton's method with this function, f, and we put in a 1.39 into our calculator, and the result was 5,391. Draw me a picture and explain what just happened. That could be a question on Friday's quiz. And what I'd want to see is I'd want to see a picture where at 1.39, here's 1, here's 2, and there was this thing, and right up here at 1.39, a tangent line went flying way out here and crossed. It was a very shallow tangent line, and it crossed the x-axis at 5,391. That's what you need to understand about Newton's method for Friday's quiz. You need to understand this process of what's going on. Okay? So that's what's going on. Now, since we got this super duper shortcut, keep hitting enter. Now keep hitting enter. And what's happening? The tangent lines are coming back, right? The next tangent line, and then the next tangent line is probably way up there at infinity somewhere. And those tangent lines are coming down and coming down. And eventually, they're coming back. And they're going to find whatever the furthest rightmost root is. 6.438. And it's exactly this scenario right here. It's exactly this. If I would have taken my first guess, it's kind of like my first guess was reasonable, but it was shallow tangent, and then it took me way out here. It's kind of like having my next guess be right here. Well, look where that's going to be. You can't even see it. Look at that tangent line. It crosses there, right? So it's coming back towards that root at 2. It's headed back there, right? It's headed back. It's coming, right? And eventually it'll get there. And that's exactly what's happening on this one. And it found that root finally. But it shot us way out there, so we got to understand what's going on. Okay, that's Newton's method. All right, get your notes out. And this is section 4.8. Okay, so in section 4.8, we've got 2 theorems we're going to talk about. And these theorems, we need to know them. We need to memorize them. Okay, so what's that mean? That means I'm going to tell you right now, well, between now and Wednesday, I'm going to tell you 3 of the questions that are going to be on Friday's quiz. I'm just going to tell you, okay? One of the questions I'm going to tell you is going to be on Friday's quiz is going to be this. State the extreme value theorem. That's one of the questions on Friday's quiz. Okay? So you might want to write that down and know that is going to be on there. You're going to have to state the extreme value theorem. Okay? All right. Now, for some of you, I'm guessing you'd much rather memorize a theorem than you would try to do a max-min story problem, so it may not be too bad. All right, here's what it is. I just noticed I kind of wrote uphill on this. The extreme value theorem, and throughout the book, questions, and so forth, a lot of times we call it the EVT. The EVT, extreme value theorem. Let f be continuous on the closed interval AB. This is kind of the if part. Now, all theorems have what's called the hypothesis and then the conclusion. The hypothesis and then the conclusion. Now, something we should talk about with theorems is one of the questions, a lot of the questions in this section that they're going to ask you is they're going to ask you, about they're going to ask you about the hypothesis and the conclusion of the extreme value theorem. Now, the title of the section is Why Continuity Matters. So, the hypothesis of the extreme value theorem is that f is a continuous function on a closed interval AB. What that means is what's about to come next only is guaranteed to be true if this first part is true, right? If you get an A in this class, then your parents will buy you a car, right? Let's say they made that promise, right? It's only a promise, right, if they follow through, right? I mean, and so if you get an A in this class, then we'll buy you a car. Well, if you get an A in the class, then they have to buy you a car, right? So, hypothesis, conclusion. But the conclusion only holds, the conclusion's only guaranteed to hold if the first part is true, the hypothesis. Okay, let f be continuous on the closed interval AB. Then f has both a max and a min value somewhere on the interval AB. Now this is called an existence theorem. It doesn't really tell us where to find it. It doesn't tell us where to look for the max and min. It doesn't tell us what the max min is. It only tells us that there is one. And all this is saying is there has to be a highest and a lowest spot. Okay? Now, we've talked about this. We just didn't make it a theorem. Here's a function, right? It's got a high spot. It's got a low spot. Right? Or here's another example. It's got a high spot and a low spot, right? Happens to be at the endpoints. Well, here's another function. Is this function continuous? Are these all continuous right here? Careful now. Are these all continuous? They're all continuous. This one's not what? Starts with a D. Differentiable. And we're going to get to that on Wednesday. The derivative is undefined right here. But continuous just means, well, there's three parts to continuous. The limit has to always exist, the function always has to be defined, and those two have to be the same. The limit has to equal the output, right? In other words, you never lift your pencil. No breaks, no gaps, okay? So if the function's continuous, you never lift your pencil, then there has to be both a max and min. Here's a max, here's a min. Now, what we did in this chapter is we said, but where do we find them? Oh, well, we find them. We look where the derivative is 0, or where the derivative is undefined, or at the endpoints, right? There's another question that could be on there Friday. I'm not guaranteeing it's going to be on there, but it could be on there. Where do we look for global max and min? Where the derivative is 0, where the derivative is undefined, at the endpoints, right? I mean, those are the three places we look. That's what we do to try to find a max and min. But that's not what this says. This just says if the function's continuous and you have endpoints, right, closed interval, then there has to be a max and a min. Now, we talked about problems where there might be a max but no min. What if you had a parabola like that? There's a max there, but there is no minimum on that. So doesn't that violate this theorem? Why not? It's not a closed interval. You're going to have a lot of questions in the homework that they're going to say, well, what about this function? This function doesn't have a minimum. Doesn't that violate this theorem? And you're going to say, no, it doesn't meet the conditions. It doesn't meet the hypothesis. This is not a closed interval. Negative infinity to infinity is not a closed interval. Right? E to the x doesn't have a maximum. Right? Actually, e to the x doesn't even have a minimum. If you just look at the graph e to the x, it just keeps getting smaller and smaller and smaller. Now, the limit is 0, but there is no smallest value on this. There is no biggest value. But it's not a closed interval. Now, if you look at e to the x from here to here, then yes, there is a max and a min. So you're going to be getting those kind of questions where they're going to say, doesn't this contradict the extreme value theorem? Well, it never should contradict. Because if it contradicts it, it means it's not true. And this theorem is true, right? What about this problem? What if I put an open circle right there? Is there a max on this? There's no max there because you keep getting closer and closer and closer, but you never get to that peak. Well, why doesn't that violate the theorem? What? It's not continuous. If you've got this open circle here, it's not a continuous function. Okay? Because it's undefined. The function is undefined at that point. So it's not continuous. So it doesn't violate the fact, so there's no max there. Well, the theorem doesn't say there should be a max there. The theorem just says, if it's continuous on a closed interval, then there will be a maximum. If it's not continuous, or if you don't have a closed interval, then all bets are off. Now, it could, here's one that really throws people off a lot of times. Does this function have a max and a min? Does the extreme value theorem promise that there will be? No, the extreme value theorem does not promise, because that is not a continuous function. Okay? It's not defined everywhere. That is not a continuous function, but it happens to have a max and a min, so good for it. But the extreme value theorem does not guarantee that there will be. It's kind of like the promise about the A. So if you get an A, so your parents say, if you get an A in calc, I'll buy you a car. So you get an A, what happens? They buy you a car, right? But let's assume they're not going to break their promise, right? So you get an A, just like this. We assume that this is not going to be kind of broken, right? This is a theorem proven to be true. Mathematicians throughout the ages, it's proven, it's good. Your parents, same thing. They're not going to break their promise. So you get an A, they buy you a car. What if you don't get an A? Huh? Now, wait a minute. Is that what they said? That's this example here, right? It's not continuous. So, does this say if it's continuous on the closed interval AB, then it has both a max and min? If it's not continuous, then there isn't a max and min. It doesn't say that, right? And same thing with your parents. Now, let's be honest. If your parents say, if you get an A, I'll buy you a car, we all kind of assume that means if you don't get an A, you're not getting the car, right? But they didn't say that, right? That wasn't part of the promise. So technically, if they say, if you get an A, then I'll buy you a car, and then you don't get an A and they still buy you a car, they didn't break their promise, right? Their promise just didn't say anything. They didn't say anything about if you're not going to get an A. If you don't get an A, maybe they buy a car, maybe they don't, right? Doesn't matter. I mean, that's not part of the promise. So the hypothesis for the promise to mean anything, for the theorem to mean anything, the hypothesis has to be true. That part's true. If that's true, then you get the car. Okay? Then the conclusion has to hold. If the first part's not true, then we don't know. So you're going to have some questions, and they're going to say, for these situations, tell if the conclusion holds. Right? So that's the situation where you don't get the A. Maybe you get the car, maybe you don't, right? So if it's not continuous or if it's not a closed interval, maybe there is both a max and min, maybe there's not. So they're gonna ask you some questions like that. Okay? Here's the second one. Intermediate value theorem. Now this one's a little more interesting, and this one you got to do a little more thinking, because this one. Well, it just got a little more to it. And here we might actually have to do a little calculation or something. So even though this is a no calculator quiz on Friday, you might still have something. Okay, the intermediate value theorem says, and this is one it's going to be a little tougher for you to memorize. Let f be continuous. That's kind of like saying if. I could have reworded that. I could have said if f is a continuous function on a closed interval. I just said let f be continuous on the closed interval AB. But I could have said if f is a continuous function. So usually we talk about this if and then, right? And if k is any number between f of a and f of b. Now, you might make a little note to yourself that f of a and f of b are endpoints, right? Those are the endpoints. Remember, because we're talking about the closed interval AB. So A is the left edge, B is the right edge. So f of a is the y value at the left edge, and f of b is the y value at the right edge. And a lot of times people mix this up a little bit. And then, okay, so k is going to be a y value. So k is some number between the y value at the endpoints. But again, same, the rest hypothesis is the same. It's got to be a continuous function on a closed interval. And I talked about this the other day, actually, when we were doing Newton's method. Then there exists some C between A and B. And then remember, A and B are X values, so C is going to be an X value. Such that F of C is equal to K. Okay, so when you, on the quiz, when you're asked to state this theorem, I'm going to want you to state it pretty much like that. Now, we're going to talk about it in a little less technical jargon. But this is how I want you to memorize the theorem. Okay? All right. So what this is saying is that if a function is continuous, and we're gonna look at a little better picture here in a minute. But if a function is continuous, because basically we said if it's continuous, you don't have to lift your pencil, right? There's no breaks or gaps or anything, right? That's what we basically said. Well, this would be f of a right here. This would be the y value, think of this. And basically what it's saying, that if a function starts here, and it goes up to here, and it comes down to here, and it goes to here, and it comes to here, and it goes up to here, or whatever. And it ends up here. Now here's where people get messed up with the f of a and f of b. Here's what the intermediate value theorem says. So if this started at, say, 2, and it ended up here at, say, 5, right? The intermediate value theorem says it had to have hit all of the values between 2 and 5. So in other words, if I started in Kearney on Highway 30 and I ended up in Grand Island, what do you know? I had to go through Gibbon, and I had to go through Shelton, and I had to go through Wood River, and I had to go through Alda, right? I had to hit all the places on Highway 30 between Kearney and Grand Island. Now, does that mean I only went from Kearney straight to Grand Island? Right? All I told you was I started in Kearney and ended in Grand Island, right? F of A and F of B, those are the endpoints. Now, I could have started in Kearney and went to Elm Creek, and then on to Overton, and then turned around, and then went back through Kearney, and then hit Grand Island, and then went on to Central City and Columbus, and then come back and ended up in Grand Island, right? I could have done all that. But if I started in Kearney and ended in Grand Island, I had to have went through all the places between Kearney and Grand Island. Now, I might have went some extra places. That's kind of all this stuff down here, right? So a lot of times people will look at a problem like this and think, well, you had to hit all the places between the minimum and the maximum. Yes, that's true. If it's a continuous function, you'd have to hit all the places between the low and the high points. But that's not what this is about. This is about the starting point and the ending point. So if you know you started here and you ended here, you had to hit all the places in between them. So I've got a little better picture of that here that we can talk about. But that's what this is saying, because it says let k be any y value between f of a and f of b. So that's saying let k be just any number here. There has to be some place that the function equals that. That's what this is saying right here. Okay, so that's why it's said this way. Let k be any number between f of a and f of b. So let k be right here. Well, then there has to be some place, and there could be more than one, right? If I went back and forth between here and Kearney, or here and Grand Island, right, I would hit Shelton a bunch of times. I could, right? But I know I had to be there at least once. If k's up here, I had to be there at least one time, right? Let k be any number in between here. There has to be a place on the function that has that as its y value. That's what that's saying right there. Okay? So, if we go and look at this here, okay, same thing. So let k be, whoops. So here's f of a, here's f of b. The green window here is everything. This function has to hit all of the y values in this green window here. So no matter where I put k, it's going to hit the blue. No matter where I put k, it's going to hit the blue graph somewhere. Right? Does that make sense? Now, why is that important? Well, Newton's method is a great example. We started off with Newton's method the other day, and we said, if I do f of 1, and I get 7, and I do f of 5, and I get -3, what's that tell you? If f of 1 is 7, and f of 5 is -3 down here, what do you know? It had to have crossed here, right? It had to have crossed here. If it's a continuous function, if it, hello? Yes. Right now? Sure. Okay, thanks. Skyler's supposed to be down in the office. She didn't say that, so I don't think so. So if it starts here and if it goes to here, then it's got to hit all the y values in between. Well, 0 is one of the y values in between. So it's got to cross. Now, what if it did this? Does it ever equal 0? No. Does that violate the intermediate value theorem? No, because it's not continuous, right? It's not continuous. So if it's continuous, it's got to hit all the y values in between. So that's a great example of why, if we know a function's continuous, that we know there's got to be a root in between there because of the intermediate value thing. It's got to hit all the y values. Okay? All right. So they're going to ask you, you're going to have a variety of different questions about that kind of thing, the hypothesis, the conclusion, right, and that kind of thing. So extreme value theorem, basically just think extreme values, max and min. Extreme value theorem is about max and mins. Okay? It has, if the function is continuous on the closed interval, there has to be a max, has to be a min. Okay? Doesn't tell us where to look for them, it just says there has to be. Intermediate, think between. Intermediate value means the values in between. So if you've got f of a here and f of b here, it has to hit all the values in between, right? If it's a continuous function on a closed interval. All right, so let's get your sample packet out. Sample 1 or sample 2, I don't care. Let's take a little bit of time to go over some questions. See what you might have there. Could be sample 1 or sample 2. These will be the first 2 we'll hand in next Wednesday, but you want to be getting most, by the middle of this week, we want to be done with these 2 packets, probably. Okay? So we work on our other 2. Number 2. Okay, the slope field for this differential equation will have vertical segments when? A vertical segment is this, right? And so what does that mean if the slope is vertical? The slope's undefined. Well, this is the slope right here, right? Y prime, right? So when will this be undefined? When that is 0, right? So when xy plus 5x equals 0, right? So how do we solve that? No. How do we just solve this equation? How do we? Well, no, that because then we get into dividing, and that'd be no good. How would you solve this equation? Factor out next. Right? Factor out next. So what do you get? X equals 0 or y plus 5 equals 0, which would be when y is -5. So either when x is 0, so that'd be on the y-axis, right? When x is 0, so the y-axis would have vertical segments, or when y equals -5. So down here at -5, you'd have vertical segments going across the right? So x equals 0. Okay? Yep. So again, little algebra. involved there, that this no calculator section, a lot of those kind of things. Oh, look at this. Look at number 3. Suppose that f is a continuous function defined for all real numbers x, and f of -5 is 3, and f of -1 is -2. If f of x is equal to 0 for one and only one value of x, which of the following could it be? Why? Why? The intermediate value theorem. How about that, right? How about now? Could you have answered that without it? I'm guessing maybe some of you answered that already and didn't have to know it was the intermediate value theorem, but that is exactly what they're talking about there. They're talking about the intermediate value theorem. Since it's continuous, it's got to cross somewhere, and if it's only going to be 0 one time, we know it's got to be 0 between there, because the intermediate value theorem says so. So it's got to be in between there somewhere. It's got to equal 0. And it says it's only going to be that once, so it's got to be that. But again, just some common sense, plot a point or two, you can get that. All right, what else? Number 11, look at this, mean value theorem. Well, guess what? I told you there were 3 theorems we were going to learn. That's the 3rd. So, you maybe, if you've got a bunch of work written down for this, then I'm pretty sure you just looked at the answer, because we have not done that yet. Okay. But we will do it. Yeah, let's look at 10. Let f of x equal e to the x squared. At how many points in the interval -a to a does the instantaneous rate of change equal the average rate of change? Very good. This is testing you on your lingo, your vocabulary. Okay, what does instantaneous rate of change mean? The derivative. So what's the derivative of this? E to the x squared times 2x. That's the instantaneous rate of change, right? What is the average rate of change? Slope between 2 points. What 2 points? The only 2 points they give you. -a and a. So how do you do the slope between 2 points? Now you subtract them. So the x's will go on the bottom. What goes on top? You have to plug those in, right? So f of a minus f of -a. Like that, right? So f of a, so if we put an a in there, that'd be e to the a squared. If we put a -a in there, -a times -a, that'd also be a squared. All over 2a, well, what is that? That's 0 over 2a, what's that? That's just 0. Oh, okay. So they wanted, that made it a lot easier. So the average rate of change is 0. The instantaneous rate of change is this, and they want to know at how many points are those equal. So all they're wanting to know is when does that equal 0, is what they're saying. Okay? But you got to understand that average rate of change is slope between 2 points. That's going to come up. It's going to come up multiple times, I'll guarantee it, in the midterm. Average rate of change is slope between 2 points. Instantaneous rate of change is derivative, right? So how do we solve this? We set each one of those equal to 0. This one's easy. When does e to the x squared equal 0? Huh? Never, right? E to the x just goes up there. That'll never equal 0. I mean, you can do the log of both sides if you want. It'll never be 0. There's nothing you can put in here. You put in 0, e to the 0 is 1. right? I mean, that's positive, but that's just, you put a negative in there, that's just gonna be, well, it's gonna square, it'll turn positive, so it just won't ever equal 0. So, at how many points does that happen? 1. And that would be between negative a and a, right? 0 would be between negative a and a. So. Okay? Good question. What else?
20.
For absolute value of x less than 1. Now, a lot of times, you don't have to worry about that right away, but it would be good, actually, if you understood that that basically meant this. That's what that means. I mean, absolute value of x less than 1. So x can't be a 2, can't be a 3, can't be a 4, but it also can't be a negative 2, right? X couldn't be a negative 2 because the bars would make that 2, and 2 would not be less than 1, or it could be negative 3, or it could be, right? It's got to be somewhere between negative 1 and 1. But all that really is 4, to be honest with you. Because if x was bigger than that, if x was bigger than 1, and you squared it, like 2 squared is 4, 1 take away 4 is a negative, you'd have square root of a negative. You can't have square root of a negative. So basically, they're giving you this just so you understand that this is going to be, right, so you don't get square root of a negative. All right? So, you don't really have to worry about that. Now, what is this? If before I do the derivative of this, I would probably, instead of writing that as square root, I would probably write that 1 minus x squared to the 1/2, like that, inside there. So how do we do the derivative of a natural log? 1 over the inside, which is the square root of 1 minus x squared. I could write it that way because I can see that's how some of those are written. And then times the derivative of the inside. Well, the inside is this, right? How do I do the derivative of that? 1/2 times 1 minus x squared to the negative 1/2 times, no, negative 2x. Right? Now, what do you notice here? You put that at 1, you put that at 1, like that. Right? This 2 would cancel that 2. This would go down to the bottom. Wouldn't that be a square root 1 minus x squared down here? Right? Wouldn't that flip down there and be on the bottom, right? So what do you got on top? Negative x. What do you got on the bottom? Square root 1 minus x squared times square root 1 minus x squared. Wouldn't that just be that right there? 1 minus x squared. Which would be which one? Now, you understand why, right? If you take a negative out of the bottom here, then that would turn into negative 1 plus x squared, right? And then that negative would cancel that negative, and then this would just be x squared minus 1. So you'd have x and x squared minus 1. So they're trying to trick you here in the sense that, like, Emily, you first said 2x, or several of you said 2x. So if you didn't have this negative here, you would end up with this one, right? If you forgot that negative, you would think it was that. Right? So you do all that good work, and then you lose it right there. Okay? So that's just a derivative rule 1, but it's got a little algebra going on in there. Okay, what else? How about 22? And I only want to do this one because it should be an easy one. So I'm hoping you look at that and you think, oh yeah, this was easy. But this is one of those that we did back in chapter 2, where So as soon as you read that, concave downward, what do you think of? Second derivative, right? You better be thinking of second derivative right off the bat. So you're going, I mean, so a lot of times we ask about the easy, the hard ones here, and we start focusing on that, and that's good. If those are the only ones we're struggling with, or the really hard ones, and that's good. Those are the ones we want to practice. Those are the ones we want to talk about. But gosh, if we're missing ones like this is where that's awful. I mean, we just can't. We can't afford to do that. If we're missing these ones that are more like our homework was, that's where we're going to get in trouble. So we want to do the second derivative. Then what? Set equals 0 and do a number line. That's right. We want a y double prime number line is what we want here. So we know that's going to be when x is 2, so that's nice. We got a 1, we got a 3. We can already eliminate some. But we plug a 1 into here, we're going to get 6 minus 12, that's negative. We put a 3 into here, 18 minus 12, that's positive. That's going to be concave down, concave up, so it's less than 2, right? So there are some questions that should be easy ones. Because if an A is a 65%, we can afford to miss a few, right? You can afford to miss a few. But you can't afford to miss the easy ones.
So does that mean like each question is 1 point?
What do you mean?
Like, so the free response, like each segment's 1
Yeah.
point.
So here's how I'm going to do it. Right. So let's say the first the no calculated one. Let's say it has 17 multiple choice questions, right? And it has 3 free response. Now those 3 free response are going to have multiple parts to them, and each part might be worth 2 or 3 points. Right now, a typical free response question is worth 9 points. If it has all of its parts intact, every AP test free response question is worth 9 points every time. So as you go through these packets or whatever, you start to understand what you're kind of getting points for. Now you don't want to spend a lot of time worrying about, oh, I wonder if I get a point for this. I mean, you just work the problem, just do it, show your work, all the things that I've been talking about, we'll continue to talk about all year long. You do that, you're going to be fine. But like on this one, if this was a free response question, you might get a point for having your derivative set equal to 0. You might get a point for this. You would probably have to write out some sort of justification, right? When y double prime is negative is when y is concave down or something like that, you know, whatever. But on multiple choice, it's just right or wrong. Yeah. So each one, Will, you're right. Each one's worth 1 point. So on these 3 free response, there might be a total of, I think on the first test we do, I think there's like 19 points in the 3 free response questions. So that'll make a total of 36 points for that test, right? So 17 multiple choice questions take up about half the test. And then the 3 free response give you about the other half. Now on the calculator section, it's a little more unbalanced. I think there's 10 multiple choice questions on the calculator section. There's 3 free response, and I think the 3 free response, now it's going to vary because I haven't decided which ones exactly I'm doing yet, but it's somewhere around these numbers here. So now the multiple choice only are about a third of the total, right, in that one. So, you know, and the only reason you'd even care about that is just so you don't spend too much time on these and not leave yourself enough time for these points down here. But yes, each multiple choice question is worth 1 point, and then you get your points in the free response section as well. And that's fairly similar to the AP test. The AP test, exactly half your grade is based on the multiple, but they do a scale and everything. Half your grade is based on the multiple choice, half your grade is on the free response. But they do one overall grade where we're going to do separate grades, you know, for each one we do. So, but yeah, that's kind of how that works. All right, let's go. So you have a little bit of work time here. Why don't we let's stop with that. So your homework then is going to be section 4.8. The 4.8 homework, it's going to be on these theorems here, basically, right? It's going to be on the EBT and the IVT for the most part. But continue to work in sample 2. Continue to work in the sample 2 packet. Now tomorrow is going to be more work time. Tomorrow's going to be, we'll go over the homework. We're not going to go on to the section 9 yet. So tomorrow's going to be go over the homework a little bit. Shouldn't take a real long time. Answer any more questions in the sample packet. Probably spend some more time on that. Then give you some work time in the packet to maybe even finish up sample 2. So go ahead and work a little more in sample 2, but mostly focus on 4.8 homework for tomorrow. Mostly. Okay? And then we'll be working in sample 2 tomorrow.